Hi, for this video, we will be discussing the applications of integration in work. In general, work is done by a force when it moves an object. If the force applied to an object is constant, then the definition of work is as follows. If you can recall from your physics, force times displacement or distance in here is equal to work. Let's try this for example. In the figure, you can see here an object being raised to a height of 4 feet. So the displacement here is 4 feet. If you're asked to solve for the work, it's basically force, which is 50 pounds, times the displacement, which is 4 feet, so that's 200 foot-pounds. But that is for a constant force. So this basically is a table showing the different units of measure for work, for force, and distance or displacement. So for us, you will most likely be using foot-pound or joules as units. Now, for integral calculus, we usually deal with what you call the variable force. When a variable force is applied to an object, calculus is needed to determine the work done because the amount of force changes as the object changes position. So for instance, the force required to compress a spring. So you might have taken this up in your physics already. So the force increases as the spring is being compressed. So let's just try to consider an object that's moved along a straight line from A to B. In this case, the displacement that you see, let's take that as delta x. The work, therefore, is basically the force times the displacement, the change in x position. So you can see that the approximation for the work is basically the summation of the individual work as you go along delta x, or basically, that's force times delta x and then get the sum of all of them. So when you translate that into an integral, you can basically have the integral from a to b of f of x dx. In this slide, you can see work done by a differential force. However, in this case, we'll be using work done in pumping the liquid out of a container. Remember earlier, the work due to a constant force is basically work is force times distance or displacement. And then in here, we'll be taking due to a differential force. That's why we will be applying the integral. So basically, that will be work is equal to force times delta S. But we have to take note. If you can recall, force is W integral of H dA. So now instead of dA, since you will be multiplying another dimension, this becomes force, the whole thing is HdA times another dimension becomes dV. So let's take this for example. You have a certain tank wherein you have a liquid inside. You want to pump out the liquid to a certain final position N. So the work done in pumping the liquid to a certain position N would have the formula W, which is the density, HdV. H is the height to which you will pump the liquid to. So from the element up to the final position. And then dV, the differential volume. The volume that you will be using now will be the volume that will be pumped out. So in this case, you might need to rotate it to get the volume using the method of discs. So let's try first. Work done to pump all the water out of a rectangular pond, 10 feet in length, 6 feet in width, and 4 feet in height to a point on the surface of the pond. And then the pond is originally filled with liquid. So let's have this. You have a pond that is 10 feet in length. So this is 6 feet in width, 10 feet in length, and 4 feet in height. So it's originally filled with liquid. So let's just say it's filled with liquid up to that height. All right. And then we need to know the work that's needed to pump out all of the liquid up to the top of the tank. So let's draw that in a Cartesian plane first. So if I were to draw that on the Cartesian plane. So let's just say, since it is symmetric, we can just draw that like this. Let's just use the right side since it is symmetric. So I'll draw an element, a certain element to represent my area. But actually, since in the formula we'll be needing volume, the element would be this element here, will be that element. I hope you can imagine the element would be sort of like a rectangular prism here. This is your dv, wherein this one would be dy. This is constant at 6. This is constant at 10. The height is the one that is changing. So that dy here will be represented in this graph as dy. And then the height to which I need to pump the liquid to is up to this point. Let's just call that the final position n, wherein y is 0 because that's the x-axis. So let's draw the points. This point is 3, 0. This point is 0, -4. This is -3, 0, but I don't really need that because I only need the right side of it. So the work is integral of w h dv. The w, the small w, is constant, so let's just use that as constant. The density, the height, we need the height, and then the dv. The height will be up to where I need to pump the liquid to, so that is 0 minus y. And then for the dv, in my case, the dv is simply length times width times height. The length, it's constant at 10. The width, for me, it's constant at 3 because I'm using only half, times the height, that is dy. So in this case, it's 30 dy. And then the question is, for the limits a to b, how much of the liquid do I need to pump out? It says there initially the pond is filled with liquid and I need to pump out all of the water. So since it's all of the water, that means from -4 up to 0. So the work done, since that is only half of it, will be w integral from -4 up to 0. H is -y. dv is 30 dy. So let's just multiply everything. This becomes -60w integral of y dy from -4 to 0. So that's -60w y squared all over 2 from -4 to 0. Let's just plug in. 4 squared 16 divided by 2 is 8 times 60. That's 480 W work units. Now let's try setting this up. Let's work done to pump all of the water out of a rectangular pond 10 by 6 by 4 to a point 2 feet above the surface of the pond. And then the pond was originally filled with liquid. So again, let's draw. So if the pond was originally filled with liquid, it's 10 by 6 by 4. Let's just draw the contents. So if it's originally filled with liquid, and then I need my representative volume, my differential volume. So let's draw this. I'll use my yellow representative volume there. And then let's draw that here on the Cartesian plane. If you don't want to multiply everything by 2, what you can do is, since it's just a rectangle, you can just make it 6 feet by 4 feet. It's just the same. Now, this was originally filled with liquid, and then you need to draw your representative element in here. But then now, what you need to do is, you need to pump the liquid to a point 2 feet above the surface of the pond. So if the pond in here, you place the surface of the pond on the x-axis. So again, x-axis, that is y equals 0. And then this is the y-axis here. And you need to pump the liquid to a certain point that's 2 feet above the surface. So n, y equals 2. So n is the final position. So I'll draw the H, that's my H. This would be my dy. Therefore, just to set up the equation, W is small w, H dv, constant, and then H up to a point 2 feet, so that's 2 minus y, and then dv, since it's just a rectangle, 10 by 6 by dy, because dy, again, it's differential height. So this one would then be 60 dy, and then the limits, since it's all of the liquid being pumped out, take note, the limits have to be where the liquid is at. So that is from -4 up to 0. Therefore, the working equation for work would be -4 up to 0, 2 minus y multiplied by 60 dy. It. Let's try another question. Work done to pump the water out of a rectangular pond, 10 by 6 by 4 still, to a point 10 feet above the surface of the pond until only 1 foot depth of liquid is left in the pond. Okay, so with that, again, 10 by 6 by 4 pond, it helps if you draw the original shape of the pond. So that's filled with liquid. And then still, the representative element will be a rectangular prism. So here, that will be your representative element. And let's just label 4 by 6 by 10. However, what we need to draw in here would be the pond is 6 by 4, but then we need to pump the water out, not all of the water out. So up to a point that is 10 feet above the surface. So here, let's just say n, y here is equal to 10. Originally, the liquid that you have, it was originally full of water, but then you will pump until only 1 foot of liquid is left in here. So this will be what's left, but what you need to pump out is the contents, the original contents. Say let's use light green will be what will be pumped out. So the original contents of the liquid were the ones in light green, and then I need to pump that out until only 1 foot of liquid is left. So this would be the height to which I need to pump it to. This is dy, and then if this is 4, I can say that this is -4, that's -3, that is 0 because this is the x-axis, and let's take this as the y-axis. So work is equal to W integral of h dv. It's constant, no problem. Height, I need to pump it to a point that's 10 feet above the surface. So 10 minus y. And then dv, that's 10 by 6 by dy. So that's 60 dy. And then the limits, not all of the liquid will be pumped out. There should be 1 foot of liquid left. So that means from -3 up to 0, all of the green shaded portion will be pumped out. And then what will be left is the blue. So that means the equation would be from -3 to 0, 10 minus y, 60 dy. So this is the working equation. Now let's try another one. Work done in pumping the water out of a rectangular pond 10 by 6 by 4 to a point 10 feet above the surface of the pond until all of the liquid is pumped out. If the pond was originally half filled with liquid. So in this case, it's no longer filled with liquid. So if this was my pond, 10 by 6 by 4, it's just half filled with liquid. So up to there only. And then I need to look for a representative element. So that's within the liquid. So let's try this portion. Okay. So if we are to draw the representative element, it would look like basically a rectangular slab. So that is 6 by 10 by dy. So let's draw the tank or the pond in a Cartesian plane. This one would be 6 feet by 4 feet. Let's use this as the x-axis. And then this one, let's assume this to be the final position, and y is equal to 10 feet. So let's shade the portion that is filled with liquid. It's originally just half filled with liquid. So let's shade half of it. And then let's draw the representative element. I need to pump out all of the liquid from the pond, but then originally it was just half filled with liquid. Let's draw the arrow where I need to pump it to from this point to that point. That's H. So that means this point is 0, -4. Halfway is 0, -2. So work is W integral of H dA. For the density, that's constant. H, that's 10 minus y because I need to pump it to a point that's 10 feet above the surface. dV is length times width times height. 10 times 6 times dy, or 60 dy. And then the limits. The limit, since I need to pump out all of the liquid, but then it's half filled with liquid, the liquid content is from -4 up to -2 only. Therefore, the work is W from -4 to -2 of 10 minus y, 60 dy. So let's go to this example. A trough full of water is 10 feet long and its cross section is in the shape of an isosceles triangle, 2 feet wide across the top and 2 feet high. So here it was drawn on the Cartesian plane where it's 2 feet on top and then 2 feet deep. How much work is done in pumping all of the water out of the trough? So here it's drawn in 3D scale, and then let's draw the representative element. In this case, it's this one. Therefore, the height that you need to pump the liquid to is just up to the surface. So up to y equals 0. Therefore, it's basically just 0 minus y. Let's write in here the things that we have learned so far. W is simply W integral of h dv. The small w is constant. H, I need to pump it to that point only, up to the surface. So that's 0 minus y, and then dv, length times width times height. The problem with this is, you know the length, it's 10. The width, it's not constant because unlike earlier where it's just simply a rectangle, here it's a triangle. So what we need here is the width would be x of the right minus x of the left. The thing is, what's x of the right? You know you have the triangle. We can use the formula for the slope. y2 minus y1 over x2 minus x1. The slope is 2, and then y minus y1 is equal to m x minus x1. I can say that y is equal to 2x minus 2, or since it's basically x that you're being asked for, x of the right is y plus 2 all over 2. So here, y plus 2 over 2 minus x of the left, that's the y-axis, that's minus 0. Therefore, 10 multiplied by y plus 2 over 2 times dy. And then what will be the limits? Since all of the liquid is being pumped out, it's from -2 up to the surface, which is up to 0. So let's see the solution in here. Yep. So we have x is y all over 2 plus 1, or y plus 2 all over 2. And then the differential volume is the one that we have. Therefore, the answer is 40 W over 3 work units. So let's try a spherical tank. What's the work done to pump all of the liquid out to a height 7 feet from the top of a spherical tank? The spherical tank's diameter was not given, so let's just assume if the diameter is 6 feet. Okay. And then place the center of the circle at the origin. So you have a spherical tank that is half full of liquid. So you need to pump the liquid up to the surface, a height 7 feet from the top of the spherical tank. So if we were to draw the representative volume would be a disk that's being revolved around the y-axis. So let's draw the spherical tank. That's 3 by 3. So since it's just a hemispherical tank, let's just draw this portion. We don't need the upper half. 1, 2, 3, 7 from the top of the tank. So that means if it's 7 from the top of the tank, the line, this one, N is 7 from the top of the tank. This is 3. So Y equals 10. So this is filled with liquid. So this one here, let's use this as the element. You will not need to multiply this by 2 because in order to get the volume, you need to rotate it using method of disks. What's the equation? The equation for this circle, x squared plus y squared is equal to 9. Okay, therefore, in order to solve, work is W HdV. The W, okay, that's constant. The H, I need to pump it to a point 10 feet from the surface, 7 feet from the top of the tank. So that's y equals 10. So that's 10 minus y. And then the thing is, for the dV, this is method of disks, where the dV is basically pi r squared dH. So we need to solve for the r. The r is basically x of the right minus x of the left. What's x of the right? It's the square root of 9 minus y squared, minus the left is 0. So this one gives us pi square root of 9 minus y squared dy. The equation for work would be W integral. Oh, we still haven't solved for the limits. The limits, all of the liquid, since all of the liquid, it should be from -3 up to 0 because this point here is 0, -3. This is 3, 0. So that means since all of the liquid, -3 to 0, 10 minus y, and then this one becomes 9 minus y squared dy. So another example here, a right circular cylindrical tank with a depth of 12 feet and a radius of 4 feet is half full of oil weighing 60 pounds per cubic feet. Find the work done in pumping the oil to a height of 6 feet above the tank. So you have here the tank that's 12 feet in height, but then it's only half filled with liquid. So it's only up until 6 feet. Now the radius is 4 feet, and then you need to pump the liquid to a height to 6 feet above the rim or above the surface of the tank. So drawing it in a Cartesian plane, you'll get these. So in order to solve for the volume, I need to revolve it, revolving it about the y-axis, and then the element would be revolved. So this is the element that we have. If I were to revolve that, that's going to form a disk. Therefore, the differential volume by r squared dh, this is for the disk. It so happened that it's just a cylinder. The radius is constant. It's 4. So 4 minus 0 squared dy. This is the differential volume. And then since you need to pump it to a point 6 feet above the surface, this one has to be 6 minus y, the height. there, 6 minus y, as you can see. And then, yep, so for the total work, it's this one. The limits would just be, since all of the liquid, it's from -12 up to -6, because the content is only up until -6. It's only half filled with liquid. Now last, a hemispherical tank that's 12 feet in diameter is filled with liquid that weighs 100 pounds per cubic feet. Find the work done in lowering the liquid in the tank by 4 feet if it's expelled at a point 3 feet above the top of the tank. So again, in order to solve for the volume, we need to use the method of disks. So let's draw this. 12 feet in diameter filled with liquid is, so you have a hemispherical tank that's 12 feet in diameter, so that means 6 0 -6 here. This is 6 0 -6 0. Half filled, or that's actually filled with, is it half filled? Filled with liquid weighs by 4 feet. Okay, so you need to lower it by 4 feet. So that means this is what's going to be left for us. We need to lower it by 4 feet. So you need to remove 4 feet of liquid. What will be left is just 2 feet of liquid. So what you need to remove is the one on top, the green shaded portion. So for the green shaded portion, let's draw the element. This is the element that we'll draw the yellow. And then I need to pump it to a point 3 feet above the surface. So up to the final point, and y equals 3. So let's draw this. That's your H. So the formula, W H dV. For W, it's given to be 100 pounds per cubic foot. So it's constant, it's given. Height, I need to pump it to a point 3 feet above 3 minus y. And then for the dV, it's pi r squared dh, because it is method of disks. So I need to rotate it. So let's just draw, rotating it about the y-axis. The element, the yellow element here, would be rotated as a disk. So the equation for this one is x squared plus y squared is 36. Therefore, x is the square root of 36 minus y squared. So for the radius, it's simply the right side of the element minus the left side of the element. 36 minus y squared, that's square root, minus 0, because that's the y-axis. Therefore, here, it's just going to be 36 minus y squared. The dh is dy. And for the limit, since not all of the liquid, even if it's originally filled with liquid, it's not all that's going to be pumped out, only to lower the liquid to that point. That means from -4 to 0 is the one that's being pumped out. So the equation would be 100, and then there's a pi. So let's move out the pi. From -4 to 0, 3 minus y, 36 minus y squared dy. So this is your equation. So let's see if it's correct. 3 minus y, 100 pi, 36 minus y squared dy from -4 up to 0. And then solving the integral, you'd be able to solve for 59,200 pi work units. So that's it.